So this is advanced classical mechanics prerequisite. Okay, so we are discussing part 2 of center of mass and radius vector. So in our last class we studied everything about 1D formulation of the center of mass. So this actually tells you where the center of mass of a system of object is in 1D, and this system contains two mass only, m1 and m2, and you can easily extend the system to a system of many masses. It's very easy. Now what I'll do is, let me tell you and let us discuss in 2D. What will be the formula in 2D? In 2D, actually you have to deal with radius vector r. Now you'll ask a question, why do we have to deal with radius vector r? The reason is, in 2D you have two code. So whenever I'm considering 2D, I'm talking about two coordinate system. So one is x, another is y. Consider two balls are placed. One ball is here, say this is 12 meter from the origin. So say consider this is the origin, and consider another ball is somewhere around here, and say this distance is 5 meter. So this two ball, one is in the x-axis and another is in the y-axis. So you can join them if you like, not a big deal. So say the join is done by a massless rod, but we don't care about the rod anyways, that's massless. So now if I ask you what will be, so consider this is of mass m1 and this is of mass m2. So the first ball that is m1 is represented by a radius vector r1. Okay, so the first ball is represented by radius vector r1, and interestingly this radius vector can be written in terms of magnitude as 12 and direction is in the j cap direction. The second ball is represented by r2, whose magnitude is 5 and it is in the x direction, that is I cap. Okay, this is the radius vector of second ball. Now the question is, what will be the radius vector of the center of mass? So imagine the center of mass is somewhere at this point, and say this point is vector r, and I have asked what will be the radius vector r such that at this point we have the center of mass. So what do we want at this point? At this point we want our center of mass. So the formulation goes as follows. What you have to do is, you have to take m1 and multiply with the radius vector r1. Remember, this is a vector equation, and I'll emphasize on this point more. Then take the second equation, mass m2, and multiply with the radius vector r2. Remember again, this is a vector, and then you add the total mass m1 plus m2. Now to give you a feeling that these two are vector quantities, so let us find what is r if m1 equals to m2. So consider a special case where both the masses are same, m1 equals to m2 equals to m. So if both the masses are same, so consider, so let me remove the 1 and 2 because both the masses are same in our example. Then what will happen? If you take m common, you will have r1 vector plus r2 vector, okay, divided by, there will be a 2m. So the answer of r, now see here you have got the r vector in terms of 12. So this will be, what is r1? R1 is 12. So because we have taken this as ball 1, so 12j plus what is r2? R2 is 5i divided by 2. So what is the radius vector? So the radius vector is, so 2.5i, okay, plus 6j. Agreed? Now let us try to understand. So when I say the capital R vector is 2.5 I and 6j, what is the meaning of that? Okay, the meaning of that is your radius vector has two components. In the x-axis it is 2.5. Try to understand. So if I draw a straight line directly from the capital R vector, then this much distance is 2.5. And what is the y? Y is 6. So if I draw a direction in this line, then this distance is your 6. So now you find R vector. Now if I ask you what is the magnitude of R, the magnitude of R will be, let us calculate from here, that will be better. So magnitude of R will be, take 1 by 2 outside, okay, and root over of will get 12 square plus 5 square, 12 square plus 5 square, so somewhere around 6.5. So that will be the length of radius vector R. So this is the length of radius vector R. But if you are clever enough, if you are very much clever enough, you will mark one thing. One mass is here, another mass is here, and there is a rod in between which is massless. And you would ask me, why the hell did you say this is 2D? Look the rod from here, look the two masses from this side. This is a 1D problem. And since both are of same mass, this is m and this is m, then all you need to find the distance of m and m. I mean m1 and m2. How to find? You see, this part is 5 and this part is 12. Agreed? So we can use Pythagoras theorem to find the hypotenuse. So this will act as the hypotenuse. So what is hypotenuse? Hypotenuse will be base square and perpendicular square. So we have a 5 square and we have a 12 square. Anyways, the hypotenuse value will be 13. So what is the value of length of this object? So length, so distance between the two masses is actually 13 meter. Where the center of mass will be? Center of mass will be exactly at the middle. Middle means 6.5. Now why I have told you this? Because this 6.5 and this 6.5 is different, although value is same, because it is one special case where the two masses are same. If you take the two masses different, you won't get these two same. This 6.5 is somewhere between these two masses, and this was not in the question. You didn't, because I didn't tell you that consider an origin somewhere around here and consider this as a 1D problem. Did I say you to do this? No. I said find me the center of mass with respect to origin here. So with respect to the origin here, this R is actually the value. This R is actually telling you where the center of mass is. Agreed? So let me continue our discussion. If I now make this problem into a three body problem. So what I'll tell you is, sort of everything. Okay. So now what I'm going to do is I'm going to convert this problem into three body problem. How? Imagine I place another body here. So the first body was mass m1, second body was mass m2, and the third is mass m3. Now if I ask you what will be the radius vector where the center of mass lies. So intuitively, let us not do the calculation, let us do intuitive thing. So join them by a massless rod. This is a rod and this is a rod, and join this. Can you tell me where, can you guess the value where the center of mass will be? Obviously somewhere around here, because at this point, if you consider this as a triangle and all these three masses are on the vertices of a triangle, and imagine they are joined by a massless rod, then obviously you can balance the triangle. This is like a ring, but it's not circular, it's just triangular. Obviously the center of mass will be somewhere in between. So you'll get the value of R here. You'll get a value of R here. Agreed? Now what formula you have to use, what modification you have to do if you are considering a three body problem? Okay, let me rub this part since you have already understood. So in three body problem, the entire equation will be this, plus you need to add something extra. The extra will be the information of the third mass. So what is the third mass? Third mass has m3, and what will be the value here? There will be an m3 r3. R3 is the radius vector from origin to mass m3. So this will be r3. This red line will be r3, and this side is r2, and this side is r1. You know this very well. So in this way you can calculate the center of mass. So I hope you understood what center of mass is. And secondly, and most importantly, what I want you to learn is about the radius vector. That's why I've taught you center of mass. This is just, I want to focus the entire concentration of how to deal with this radius vector, because in the advanced classical mechanics will be dealing with n particle system, and their radius vector, and understanding the radius vector becomes very important. Agreed? So what I want you now focus is look at this particular note. So you can see here there are three objects, a mass here, and another mass is at the origin. Agreed? And you are so what is this? 8 kg, this is 4 kg, and this is 3 kg. Now if you are asked what is the center of mass, what is the radius vector of center of mass, so what to do? Calculate individually x and y as you have done here. So what is individual value of x and y? See, the 3 kg has x0, y0. The 4 kg has x2, y1, and the 8 kg has x1, y2. So what you need to do is multiply all the masses with their x coordinate and add the masses. So here you got the x coordinate of this r. Second, to find the y coordinate of this r, add all the masses and their y coordinates is 0, 1, and 2. These are all the y coordinates. So y coordinates, and add all the masses. So this is the y coordinate of the center of mass. So where is the center of mass? The center of mass is somewhere here where I have kept the cursor. And what is the coordinate of the center of mass? This center of mass has a x coordinate at 1.1 meter and a y coordinate at 1.3 meter. Agreed? So I guess you understood how to calculate center of mass. Look at this problem carefully and solve it yourself. Agreed? Now what I'll tell you a very interesting thing. The interesting thing goes as follows. If an object was initially at rest and say it explodes, then the particles of that object will move in such a manner that center of mass is constant. For example, consider an initial mass m, and consider somehow there was an explosion, and after this explosion this m got converted into two masses. One was m1 and another is m2. So m1 and m2 are two fragments of the capital mass m. So if you add m1 and m2, you will get again m. So that's why I said exploded. So when it exploded, it got divided into two bits. Okay, and this m2, say it moves with a velocity v2, and this part also moves with a velocity v1. Now an interesting thing, can you tell me what was the center of mass? So since this is 1D, so let me not write r, so it's better I write x. So can you tell me what was x before explosion? The object was at 0, so consider this part as 0. So object was at origin before the explosion. Now after the explosion, so this is before the explosion, so after the explosion there will be a conservation of the position of center of mass. So center of mass is going to be same. Now center of mass is going to be same, it means that the m1 x1, so m2 x2, divided by m1 plus m2 is going to be 0. But try to understand, should I write a plus sign? No, I should write a minus sign. Why? Because both are going in the opposite direction. One is going in the plus x direction and another is going in the minus x direction. So let me, where should I put the minus sign? So your v1 is going, so I should put a minus sign here. So let me put a minus sign here, and this will be a plus sign. Now it's okay, because v1 is going in the negative x direction, so my x1 will be negative, and v2 is going in the positive x direction, so my x2 is positive. So what this equation leads to? This equation leads to m1 x1 with a minus sign plus m2 x2 equals to 0. If I differentiate this equation with respect to time both sides, what will happen? Nothing, everything is okay. You can do this part. So what will happen? This will act on x1, and what do you get? You'll get m1 v1, and then differentiation will go and act on x2. What do you get? You get m2 v2 equals to 0, and finally you have m1 v1 equals to m2 v2. So forget this part and concentrate more on this part. You see, the conservation of the position of center of mass before and after collision indirectly gives you the conservation of momentum. If you look at this equation, it is nothing but conservation of momentum. Okay, so forget center of mass here. Tell me, let us do the momentum. So what was the initial momentum? The initial momentum is 0. What is the final momentum? Final momentum is m2 v2 minus m1 v1, because the direction of v2 and v1 vector is opposite to each other, and by law of conservation of momentum, initial momentum of the system and final momentum of the system will be same. So by conservation of momentum, I should have m2 v2 minus m1 v1 equals to 0. So what you see, an amazing thing here is the conservation of the point of center of mass before and after explosion indirectly leads you to the conservation of momentum. Quite interesting, right? So what do you understand from this discussion? You understand that if an object has a center of mass 0 before explosion, then after explosion all the particles will have masses and velocities such that when you add them, you have the final center of mass at position 0. Always. It's not going to change with time. It's going to be always 0. Agreed? So if I now tell you, let us take a special case to understand this part. If both the masses are same, so consider after explosion both the masses are same, then what will happen? This is same, this is same. Then by this equation, both the velocities will also be same. This will be same as this. So if the object explodes into two equal masses, then these two equal masses will move away from each other with same velocity, so that the either you can say so that the conservation of momentum is maintained, so that the conservation of momentum is equation for conservation of momentum is maintained, or you can say so that the center of mass position is maintained before and after collisions, because both are same thing. If you say center of mass of a isolated object is always constant before and after collision, this statement is same as saying that there is a conservation of momentum in our world. Agreed? So we'll discuss more with the advanced classical mechanics in our next class.